Hi everyone, let's continue section B of the 2024 physics exam. Question 9. Students build a simple DC electric motor consisting of a single coil of wire in a uniform magnetic field. The coil is initially at rest and orientated in a horizontal position as shown in figure 11. The coil can be rotated about the axis of rotation shown. Alright, so it's a coil. It can rotate along the dotted line. It's connected to a voltage source of 6 volts and it is initially at rest in that position. Part A, describe one orientation of the coil, if any, where the magnetic force on side FG here is 0. Justify your answer. Okay, so we've got a current flowing through this coil. We can imagine, so this is 6 volts driving a current like this around, at least in that position. Okay. We know from theory that when you have a current within a magnetic field, that current will experience a force anytime that current has a component perpendicular to the magnetic field. Okay, if the current is parallel to the magnetic field in any way, then no force will be given to that current. Okay, so the position that it's in right now will actually be an orientation where the magnetic force is 0 on FG. Okay, so I mean we can just say that when FG is parallel to the field, the coil, because it's asking for the orientation of the coil, not the orientation of FG, we have to specify what the coil will look like. When FG is parallel to the field, the coil is horizontal. Since FG is parallel to the field, I probably could have not written this first part here, but we'll just leave it for now. Since FG is parallel to the field, it will not experience... Actually, I'm not happy with the way that I'm writing this. I'm going to just pause it and come back after I've finished writing my answer. Alright, so I've just rewritten my response there. FG will experience no magnetic force when it is parallel to the magnetic field, and this occurs when the coil is horizontal. Okay, I like that wording much better than what I was doing. Okay, hope that makes sense. Let's keep going. B. Describe one starting orientation of the coil, if any, where the coil will not start to rotate from rest. Justify your answer. So the coil will not start to rotate from rest when it is vertical, and why would that be the case? If that was the case, if it was vertical, then there would be currents flowing through sides EF and GH. Okay, but those currents would be running anti-parallel to one another, so in opposite directions to one another. Both of them would be perpendicular to the magnetic field, but because the currents are running in opposite directions, the forces on each of those currents would be straight up and straight down. Okay, and you could sort of prove that with your slap rule. But basically, when the coil is vertical, the force on so I'll just start writing it out. So when the coil is vertical, I'll just say when the coil is vertical. That's the starting position. When the coil is vertical, but why? So now I explain why. Okay, when vertical, the force on side EF is opposite. Don't specify up or down because we don't know the direction of the current. Could be vertical in one position, vertical in the 180-degree position. The force on the side EF is opposite that on GH. And if vertical, no torque is applied on the coil. Okay. I guess if you really wanted to, you could also talk about FG and sides EH, but that would have the same sort of explanation as what's going on here. It's just there's no the main point that you want to get across in this question, I think, is that there's not going to be any torque applied on the coil. So there's not going to be any turning of the coil, simply because the coil is in rotational equilibrium. And that's it. That's all you've got to really talk about, I think. So we specified the orientation and we specified why. And really it's just, yeah, the no torque. Part C, suggest one way that the torque of the DC electric motor could be increased using exactly the same coil and the same 6-volt battery as shown in figure 11. Well, it doesn't say anything about keeping the magnets the same, so I guess if it's only one mark, you could just say use a stronger magnetic field. Okay, because then that would increase the force on the sides of your coil, and then that would increase the torque, I guess. So use a strong magnetic field. I don't think there's any other way that we could do it if we have to keep everything else constant. The coil has to be the same, and the battery has to be the same. Yeah, there's nothing else I can really do. Just get stronger magnets, I guess. Use a stronger magnetic field. Alright, that's it for question 9. Question 10. Two students, Aroha and Taylor, are investigating electromagnetic induction. They use the apparatus shown in figure 12, which consists of a single coil of wire and a uniform magnetic field connected to slip rings X and Y. Explain the purpose of slip rings as shown in figure 12. So every time I see this question, there seems to be a slightly different way or a slightly different phrasing of what the examiners are looking for. But most often, on average, they're looking for it allows continuous rotation, or allows for a continuous output, let's say. Okay. Allows for a continuous output. That's one thing, okay, continuous output. It's not like a jagged start-stop output. And also the second thing that we're looking for, it's a continuous output of AC voltage or power or whatever they're looking for. Okay, I'll just say AC power. So it's those two things, continuous output and AC power. I think that's the main things that they're looking for in a response like that. Okay, don't go into it. Don't say, oh, slip rings are there so the wires don't get tangled up and all that kind of nonsense. Obviously, we don't want the wires to get tangled up. That's not the point. Okay, they want to say, what are the slip rings doing to the output of your oscilloscope? Right, it's going to produce a continuous alternating current output. Right. So keep it simple. Don't go into crazy detail. Just leave it like that. Part B. Taylor rotates the single coil of wire within the uniform magnetic field at a constant rate, while Aroha measures the output voltage E versus time t on an oscilloscope. The oscilloscope display is shown in figure 13. Okay, there's your continuous AC. From the oscilloscope trace shown in figure 13, determine the peak-to-peak voltage produced by the apparatus and the frequency of rotation of the single coil. Alright, so this should be pretty straightforward. Peak to peak, you should know what that is from theory. It's just the difference between the highest and lowest points of your output. So that seems to be from 4 to negative 4 volts, so that's just 8 volts. The frequency, that comes from the period of your graph, so one period is from there to there, which is 0.2 seconds, so the frequency is 1 over 0.2, which is 5 hertz. Okay, don't need to do any working out, I mean, unless you want to show that for your frequency, but just have to put the numbers in the boxes. Part C. Taylor makes a modification to the apparatus in Figure 12. Aroha sees the new oscilloscope trace as shown in Figure 14. The dotted line shows the original voltage before any changes are made by Taylor. Explain two possible ways that Taylor could have modified the apparatus to create the oscilloscope trace shown in Figure 14. Justify your answers. So what's different? So here's our dotted line, that's the original. Okay, it has a peak to peak, or amplitude of 4, let's say. The new graph has an amplitude of 8. Still seems to have the same period. Okay. Now, if you imagine someone rotating a coil faster, that would definitely produce a larger voltage, because the EMF, according to Faraday's law, is equal to the change of flux. And we're actually going to use this to answer the question, but change of flux over change in time. Now, if you're rotating faster, this change in time gets smaller and smaller, right? The period gets smaller, so your EMF jumps up. But we can't be doing that because the period stays the same between the two graphs, okay? So we're not doing anything to the period of the rotation. We're not changing the frequency or anything like that. The only thing that we could be doing is playing around with the flux, but I also neglected N. N is the number of turns in your coil. Okay, so does it say anything about? Okay, Taylor rotates a single coil of wire, and then it just says Taylor makes a modification. So it doesn't say anything about the coil having to be constant. So we could, and by the way, flux is magnetic field strength times area. Okay. So, explain two possible ways that Taylor could have made a modification to the apparatus. Well, Taylor could have well, we have to be specific here. Okay, the voltage has doubled. It hasn't just increased, it's doubled, a very specific number, right? So it doubled. So we could double N. Alright, now if N originally was 1, it was a single loop of wire. Okay, we could say that Taylor then used 2 loops of the coil. Right, that would double, since EMF is proportional to N. And a second thing that we could have done, so well, I mean, there's two things really. You could increase the magnetic field strength B, or you could double the area A. Let's just say we double the magnetic field strength. Okay, so we double the magnetic field strength. B, again, since EMF is proportional to B. Alright. I wonder if I should mention anything about the area. It says it's 3 marks. Use 2 loops of the coil. Okay, I think the 3 marks come from, so 2 marks are from the 2 possible ways, and then the 3rd mark is justifying them, which I think we've done. I think the fact that we've written down that they're proportional to them, I mean, if you really want to, you could just write Faraday's law, just to be very clear that you're showing the examiners you know where this proportionality is coming from. EMF is equal to N delta flux over delta T, which is equal to N delta B A over delta T. All right. I don't think there's much else that we could write there to prove to the examiner that we know what we're doing. But I think the main thing is you don't just say use more loops or use a stronger field. You have to be specific. Okay, you are doubling the EMF. Okay, so you have to say use 2 loops instead of 1, or you double the field strength. Okay, and I think that is what they're looking for in order to award those marks. Question 11. GR charges a 60, oh my god, 60. Gia charges a 36 volt battery used for her electric bicycle from a mains 230 volt RMS power point. The transformer part of the battery charger circuit is shown schematically in figure 15. Assume that the transformer is ideal. No power loss, no energy loss. Alright. Calculate the number of turns required on the secondary coil if there are 460 turns in the primary coil. 1 mark. This should be very easy, straight from the theory. You've got your transformer equation. Let me write it out quickly. V primary over V secondary is equal N primary over N secondary. We want N secondary. Doing a bit of algebra, you get, what is it, NP Vs over Vp. Okay. Chuck your numbers in. Where am I? NP is 460. Vs is 36 and Vp is 230. Okay, even if you didn't have a calculator, you could probably work this out. 72, because that cancels with that. That becomes a 2. 2 times 36 is 72. And there you go, done. 1 mark, less than 1 minute. Part B. The RMS output current from the transformer to charge the battery is 0.8 amps. Calculate the RMS input current to the transformer. Okay, so we've worked out the number of turns. You don't really even need to use the number of turns here. All you need to know is that it's an ideal transformer. I mean, so there's multiple ways of doing this question, but you could use the transformer equation. Let me just show you the options that you've got here. So you've been given IS and you want IP. Okay, from previous questions and data, you've got VP, VS, you've got NP, we've worked out NS. So you could use any of the transformer equation variations, but I think the easiest thing is to just notice that it's an ideal transformer, so you're not losing any power, right? So the power that you have on one side of the transformer should be the same as the power on the other side. So I'll go PP equals PP. All right, PP equals PS. What does that mean? It means VPIP equals VSIS, and we want IP. I don't want to P. IP. That's VS over IS over VP. Okay. So VS was 36. IS is 0.8. And VP was 230. And you end up getting 0.125 amps. Significant figures. I mean, we've got 3 here. That's 2. These are 3. That's 2. I mean, you could probably leave it as 3 and then they're not going to penalize you. I'll put it as 2. So we'll just say 0.13 amps. As long as you got that sort of written down there, they're not going to... They shouldn't penalize you, okay? Because you've shown that you know what to do here, okay? Again, it's not a significant figures question, okay? It's a question about transformers, okay? They're not looking for significant figures here. They're just saying, do you know how to work with transformers? All right. Part C. Explain why the transformer requires AC input and would not work if the input was constant DC. Okay, why does the transformer require AC input and it would not work if the input was DC? Okay, so there's two things they're looking for in your explanation. Why does it require AC, and why wouldn't it work if the input was DC? Okay, so it requires AC for a constantly... Actually, you know what? I'm going to pause here. You don't like watching me write in silence. I'll just pause it and come back. Alright, so there's my response. So let's have a read. So your transformer requires AC for a constantly changing flux in the primary coil, which induces a constantly changing flux in the secondary coil, and thus an induced AC current in that secondary coil. DC would not vary in time, so there would be no way to induce a current in the secondary coil apart from perhaps switching the input on and off. Okay. The key point here is that you need a way to sort of constantly have a constantly changing flux in that secondary coil, and that is only possible if you have a constantly changing flux in the primary coil. So that flux sort of propagates through that iron core of your transformer. And I think that response is sufficient. All right. Question 12. A general store in country Victoria is connected to the mains 230 volt electricity supply. The owners decide to install an array of solar photovoltaic panels to decrease their electricity bills. The maximum output of each PV panel is rated as 600 watts in full sunlight, with a maximum voltage output of 20 volts. The owners install 50 PV panels connected in a 10 by 5 array as shown in figure 16. Cool. The array consists of a bank of 5 strings connected in parallel, so that's your 1, 2, 3, 4, 5, with each single string consisting of 10 PV panels connected in series. The total output of the array is connected to an inverter. Alright, part A. Calculate the maximum possible total output power from this array. Give your answer in kilowatts. Alright, so total power output, well, I think that the easiest way to say that would just be we've got 50 panels and each panel can generate 600 watts. I don't think it's any more complicated than that. It's only one mark. It makes sense. You've got 10 panels here producing a bunch of power. When it comes to power is sort of additive in circuits. It doesn't have the same rules as like series and parallel where you've got to do like fractions and stuff. Power is just additive, right? So we've got 50 panels all together. Each one generates 600 watts. So really just the power is 50 times 600, which is 5 times 6 is 30,000 watts, which is 30 kilowatts. Okay. Your box has kilowatts already, so just be careful there. Part B. Calculate the maximum output voltage and maximum output current from one string of 10 PV panels connected in series in full sunlight. Show your working. Okay, so if we look at the picture, I mean, you've got these 10 panels in series. When you've got voltage sources, which I guess this is what they are, in series, you just add up the voltages, I guess. So you've got 10 in a row. And it says each, in the description, the maximum output of each panel is a maximum voltage output of 20. So it's the maximum voltage for one string of panels is just 10 times 20, really. So we can say that the total voltage V is just 10 times 20. Okay, 10 panels in a string, each one has a maximum voltage of 20. It's 200 volts. Now, what's the power generated from all of those panels? Well, you've got 10 of them in a row, and each one generates 600 watts. So 10 times 600 is 6,000 watts, and then from that we can get our current. Okay, because it didn't say anything about current. There's nothing about current anywhere. Okay, so the only way that we could work out current is we've got the voltage from all of those things and the power from all of those things, and then use P equals IV. So that means current is equal to P over V, which is 6,000 over 200, which is 30. Okay, I hope that makes sense. Just go back and rewatch that if you didn't get it. Part C, determine the excuse me. Determine the maximum output voltage and maximum output current from the whole array in full sunlight. Okay, so we've worked out in part B that one string has a maximum voltage output of 200. Now, all of these strings are in parallel with one another. Voltages in parallel do not add together. They've all got the same voltage, okay? So the maximum voltage is still 200 because everything's in parallel. However, the current, when you're talking about parallel circuits, the current becomes additive. So you've got a bunch of current being generated in this string, and then it comes into here at this junction, and all of this current generated here then gets added to that current at that junction, and they travel off down here, and then all of this current generated in this string enters chat, and then, you know, like it all adds up together at the end. So current is additive when we're talking about parallel. Now we've got 5 strings in parallel. From part B we worked out the maximum current is 30, and so 5 times 30 is 150. And that's only one mark, so I don't know which part they're going to give you the mark. I mean, 200 you didn't do any work to get, so that should just be given. Maybe the mark is only really for doing that. I have no idea. Okay, so yeah. Anyway, D, what is the function of the inverter? So again, this just comes straight from notes and theory. All of these are like batteries, right? So batteries in series, and all of this can be treated as one single battery, and then you've got 5 of those batteries in parallel. Batteries are DC, okay? For any, you know, real purpose, we want our electricity to be in AC. So the function of an inverter is simply just to convert DC power to AC power. That's it. 1 mark for that. Question 13. When energetic cosmic rays from space interact with Earth's upper atmosphere, subatomic particles known as muons are produced. These muons are unstable and have been observed to decay rapidly. They decay with a mean lifetime of 2.2 microseconds. As a result of their short half-life, physicists have used the muons produced in the Earth's upper atmosphere to test Einstein's special theory of relativity. In one experiment, physicists placed a muon detector at the top of a mountain at a height of 6,500 meters. The muons produced in the upper atmosphere at a height of 9,700 meters above the Earth's surface traveled downwards at a speed of 0.985 c. This is shown in figure 17. Okay, so what's happening is you've got muons coming, or cosmic rays coming down, interact with the atmosphere, generate these muons. The muons continue their journey at speed 0.985 c, and they just continue down. Now we've got the upper atmosphere at 9,700 meters. There's a muon detector on top of this mountain, 6,500 meters. That's your setup. All right. Using classical mechanics, show that a muon would reach the muon detector at the top of the mountain in 10.8 microseconds. All right. So the muons are traveling a particular speed. they would require to travel a particular distance. That's this difference here. And we're required to show that in order to travel that distance at that speed, it would take that much time to happen. So that's just a speed, distance, time question. So we're required to show the time. So we say time equals distance over speed. The distance required to travel is the difference between these heights. So 9,700 minus 6,500 over the speed of the muons. Speed of the muons are given as a fraction of the speed of light. So it's 0.985 times the speed of light, 3 times 10 to the 8. And if you put it on a calculator, you get 10.8 microseconds. Again, the only thing they really want you to do is write this down, okay, for 1 mark. Part B, according to classical mechanics, is a muon likely to reach the muon detector at the top of the mountain? Justify your answer. Okay, so we know that they would have to take this long to get to the detector. However, their mean half-life is 2.2 microseconds. So, I mean, that would mean that, you know, how many, okay, so let's work out how many half-lives are in 10.8 microseconds. So, I'll just say 10.8 microseconds is around 5 half-lives. I don't think we have to be very precise here. So, I don't even know how precise we have to be. Is a muon likely to reach the detector at the top of the mountain? Justify your answer. Well, in 5 half-lives, that means you've halved the amount of muons 5 times. So only, I mean, you probably don't have to be this precise with your maths, but so only around 1 in 2 to the 5 muons will be detected. Most muons will have decayed by then. Okay, I think that's sufficient. I mean, you probably don't have to go into around only 1 in 2 to the 5 muons. I mean, that's very mathsy. You don't probably have to worry about that so much. You just say, look, 5 half-lives have passed almost. Most muons would have decayed by then. So they are not likely. So I'll just say, therefore not likely to be detected. If that wasn't obvious already, examiners. There you go. Okay, so that's what I'm going to say. Use the following information to answer parts C, D, and E. Experiments conducted by physicists show that a significant number of muons created at a height of 9,700 meters above Earth's surface and traveling at a speed of 0.985 c consistently arrive at the muon detector at the top of the mountain. Part C, calculate the Lorentz factor for a muon traveling at that speed. Okay, so very straightforward question. You have an equation for your Lorentz factor. It's 1 over the square root of 1 minus your fraction of the speed of light squared. So 0.985 squared. Chuck that on a calculator, you get 5.8. Okay. Significant figures, let's not stress about that too much. 5.8. They're looking for, have you got the right equation? Have you got roughly the right number? D. What is the mean half-life of the muon in the physicist's frame of reference? Now, I've already looked at the examiner's report because I don't want to make too many mistakes when I'm doing this exam for you guys. I've already done it blind. I just checked my answers afterwards. But the examiner's report states, and let me see if I can bring it up. Just give me a second. All right, so here's the report. If I scroll down to 13D, they say something really interesting. I really wish I went to the conference or I was an examiner this year or an assessor. But it does say, very interestingly, as a result of psychometric analysis and review, all students were awarded full marks for this question. I have no idea what that means. I have a feeling that the question was ambiguous, and also the fact that it was only 1 mark. And the reason for me saying this is that in your question header, it says the muons decay with a mean lifetime of this, which wouldn't you think that is what what the physicists say the muons decay in, right? I'm pretty sure the question's asking you, now that the muons are traveling at this speed, like that this would be the proper time for the muon's half-life, and what the question's asking for is what is the dilated time for the muon's half-life. So I think a lot of students might have just put that original number there, maybe, and because it's only 1 mark, they didn't have to show working out. But a lot of students might have done the dilated time and put their answer here, and it's only 1 mark. I have a feeling that's what happened. I've contacted VCAR at the time of making this recording. They haven't responded back yet. I've asked some other colleagues. They don't seem to know either. But as soon as I get a response, I'll put that information in the description of the video as to why everyone was awarded that mark. But I mean, let's do it the way that I think that they intended doing it. So I mean, you've worked out a Lorentz factor for these muons. So the half-life, the dilated half-life, according to, like, imagine the muons were wearing these little watches. They would decay within 2.2 microseconds on their own watch, but according to the physicist watches, how long will it take on the physicist watch for the muons watch to read 2.2? That would be the dilated time here. So we would just say that we do 5.8 times 2.2 microseconds, and I'm getting 12.8 microseconds. There's also no box to put the answer in, but I don't think that's neither here nor there. I think this just was maybe a poorly chosen question and a poorly phrased question. So I think everyone just got a mark for that. But it doesn't really matter. Let's just move on. Part E, explain how Einstein's special theory of relativity accounts for the experimental evidence that a significant number of muons created at a height of 9,700 meters and traveling at that speed consistently arrive at the muon detector at the top of the mountain. These questions are very common. They're saying classical physics said they shouldn't be appearing. They are appearing. Why are they appearing? What specifically part of special relativity can explain why they're appearing? And there are 2 ways to answer this question. Many times students, in my own class as well, they seem to say, they use both reasons at the same time, but they mix them up, and they end up sort of contradicting themselves in their response to the question. So there are 2 ways that you could do this. I'll point them out. You could use length contraction. Okay, length contraction. And what do I mean by this? Well, if you imagine the 2 points between the muon's creation and their detection, the muons are traveling, and imagine this length here is a stick. The muons are traveling parallel to that stick, so according to the muons, that stick will appear contracted to them. So the distance that the muons have to travel in their own frame of reference is shorter. And so that means they are probably able to get to the end of that distance before they decay. The other way to see it is using the time dilation, or the dilated half-life of those muons, okay, which I guess is what this question here was trying to get to, but for whatever reason wasn't very clear. And you now say, okay, they still have to travel that distance of 3,200 meters or whatever it is, but they're allowed to live for longer. They don't decay as quickly, so they exist for longer before they disappear or they decay, and so more of them reach the end. So these are two separate reasons. Okay, don't mix and match them, because one is from the reference frame of the scientists or the detector. One is from the reference frame of the muons. So the dilated half-life is from the reference frame of detector, whereas the length contraction is in the reference frame of the muons. Okay, you can't mix and match reference frames, so don't put both reasons in the same response, otherwise you're going to be contradicting yourself. So if you're talking about length contraction, I'll probably stick with the length contraction one, to be honest. So you say length contraction, the distance the muons need to travel appears contracted in their own frame of reference. Again, sorry for the writing and the silence. Okay, so the distance the muons need to travel appears to be contracted in their own frame of reference, and so more muons are able to travel this distance before decaying. So a larger proportion are detected. Okay, now just again, we're going to see if we've answered the question. So explain how Einstein's special theory of relativity accounts for the experimental evidence that a significant number of muons, blah, blah, blah. Okay, so it doesn't say, and why doesn't classical physics explain that? So that's fine. So we've said length contraction. I might also add on to that length contraction is a consequence of special relativity. Just to be clear, we are using special relativity when we're talking about length contraction. But it should be clear. I mean, the examiners aren't dumb. They know if you know length contraction, you're dealing with special relativity. But yeah, the main thing is that according to the muons, the distance they have to travel is shorter. Therefore, they're able to travel that distance before they decay. That's it, okay? If you want to do the other response, the dilated half-life, you can say that according to the scientists, the muons have a longer half-life, meaning they're able to cover that distance before they decay. So it's pretty much the same, like this dot point here would be the same for both types of response. It's this dot point here that would be different. That you would say, on this side, you would say the half-lives of the muons, according to the scientist frame of reference, are longer than in the reference frame of the muons, or something like that. But I would just think with the length contraction one. I think that's a bit more clear. Yeah. All right, let's move on. Question 14. PET, positron emission tomography scanners are used in medical imaging. They rely on an electron and a positron colliding and completely annihilating each other to produce two gamma rays. The electron and positron have the same mass. Assuming that the electron and positron are traveling at a negligible speed when they collide, calculate the total energy released in the annihilation. Okay, so when I saw this, I thought, okay, you've just got things that have mass being destroyed and turned into energy, and that sounds like E equals mc squared to me. So the energy released is equal to the total mass times c squared. The total mass involved in this collision is the mass of the electron and the positron, and it says that they have the same mass, right? So it's going to be 2 times the mass of the electron, 9.11, times 10 to the minus 31, times 3 times 10 to the 8, not 9, squared. Chuck that on a calculator, you end up with 1.64 times 10 to the minus 13 joules. Okay. Significant figures, no, leave it as 3. There's no numerical data in there apart from mass of the electron. There you go. The two gamma rays produced travel in opposite directions with exactly the same wavelength and energy, as shown in figure 18. Explain why the gamma rays travel in opposite directions. Well, again, when I saw this, I'm thinking, okay, there's 2 objects colliding. These 2 objects have the same mass. So if they have the same mass, then the velocities kind of have to, no, that's, now that I think about it, it's not the way that I would word it, but I would say that they travel in opposite directions purely to preserve or conserve momentum, because even though the electron and positron have annihilated each other, there's still momentum there, right? You can't just sort of get rid of momentum, right? So you know, it's only 1 mark. The easiest way to explain something like that is just to conserve momentum in the collision. Right? That makes sense. I mean, the gamma rays themselves, they do have momentum. Gamma rays are photons of some kind, and we know from theory that photons have momentum. But yeah, I mean that's all we need really for 1 mark to conserve momentum in the collision. Don't need to talk about energy being conserved. We already know energy is being conserved. It's more just why they're traveling in opposite directions. Why isn't one going that way and one going that way? They have to be completely opposite one another, I guess. I mean, I don't want to spend too much time on this, but yeah, you know what? I'm just going to leave it there. I don't want to get into the nitty-gritty details when I don't need to, so I'm just going to stop there. It's to conserve momentum in the collision. Question 15. An electron gun forms part of a transmission electron microscope which uses the wave properties of electrons to study specimens that are too small to be observed using an optical microscope. Figure 19 shows a beam of electrons passing from an electron gun through 2 plates, plate A and plate B. Okay. The electrons reach plate A with negligible speed and are accelerated by the potential difference between the plates V0 emerging from plate B with a speed V. The de Broglie wavelength of the electrons in a particular beam is that. Calculate the momentum of an electron in the beam. Okay, so we have a formula for this. De Broglie wavelength is related to momentum via this formula here. It's important to know that when we're dealing with things that we classically think of as particles, like electrons and things like that, we have to use the joule seconds version of H. not the electron volt seconds version of h. So h here is going to be 6.63 times 10 to the minus 34 over the de Broglie wavelength. Chuck it on a calculator, 2 marks, you get 3.32 times 10 to the minus 24. Okay, easy. B. The electron beam is passed through a crystal with an interatomic spacing of this. Two physics students, Sally and Max, are discussing their prediction for diffraction patterns produced by the electron beam. Sally claims that since the wavelength is less than the interatomic spacing, there will not be a detectable diffraction pattern formed. Max disagrees and claims that they will obtain a useful diffraction pattern. Who is correct? Okay, so let's compare the spacing to the actual wavelength. So when looking at whether or not diffraction is going to show its face, like whether or not you're going to notice diffraction, it's really when the gap or the aperture or the opening of whatever, whether that has a width that's roughly the same order of magnitude as the wavelength. Don't get bogged down in the actual numbers themselves. It's the order of magnitude that we're dealing with. Okay, so we'd say diffraction occurs, and you know what, I'm going to pause it here and write. I'll come back in a second. Alright, so I've said diffraction occurs when the wavelength and aperture, or the wavelength and the spacing of your crystal or whatever, are of the same order of magnitude, which is the case here. And thus Max is correct, they will have a useful diffraction pattern. Okay, so just keep that in mind. You will have diffraction when your wavelength and the gap width are of the same order of magnitude. Don't get worried about the numbers, or that's 3 but that's 2. It will lessen the effect, but it will still be there. Okay, it's like, yeah, don't stress too much about the numbers. Okay. All right. So parts C and D. Sally and Max now change the potential difference in the electron gun to generate electrons with an energy of 600 electron volts and a corresponding de Broglie wavelength of this. This adjusted electron beam is then directed through a thin foil, resulting in the diffraction pattern shown in figure 20a. The students decide to contrast this pattern with the pattern produced by passing X-rays through an identical foil shown in figure 20b. They note that the electrons in the X-rays produce patterns with the same dimensions. Okay, so the same, I guess, spacings between the rings that you see here. Part C, explain how the electrons and the X-rays can produce almost identical patterns. Alright, so you can say something along the lines of the spacings between the rings and therefore the patterns are a result of diffraction, and the amount of spacing between the rings is a result of how much diffraction is occurring. Now, how much of diffraction is occurring is a result of the wavelength of the thing that is diffracting. So if they're producing the same pattern with the same spacings, then we can conclude that the X-rays and the electrons must have the same de Broglie wavelengths to diffract in the same way. Okay, so how you want to phrase that is up to you. I'll pause it here and write my response, and then we'll move on. Alright, so I've just said the spacing of the diffraction patterns is determined by the wavelength, and thus the electrons and X-ray photons must have the same wavelengths. Okay, so 2 key points. Spacing depends on wavelength when something diffracts, and because the 2 pictures are identical, then they must have the same wavelengths, right? Part D, calculate the energy in electron volts of the X-ray photons used to produce the image shown in 20b. Calculate the energy of the photons used to produce the image shown. Okay, so because they're producing the same image, we know that they have the same wavelengths. We've been given the de Broglie wavelengths of the electrons this must also be the wavelength of the X-ray. So we can say the wavelength of the X-ray is equal to 5.01 times 10 to the minus 11 meters. Okay, now how can we get energy from wavelength? So we can use the formula photon energy is equal to hc on lambda. H is Planck's constant. Because we want our answer in electron volts, we can use the electron volt second version of H. So that's 4.14 times 10 to the minus, minus 15. C, speed of light, and lambda here is our wavelength, which is the same as the de Broglie wavelength of the electrons. Chuck all that on a calculator. You will get something around 24790 electron volts, but you can play with that and turn it into, how many sig figs do we want? That's 3, that's 3, let's do 3, so 2.48 times 10 to the 1, 2, 3, 4 electron volts. There you go. Cool. So the key idea here was to notice that because they're the same pattern, hopefully you would have identified that in part C, that the photon wavelength must be the same as the electron de Broglie wavelength. And then you can use this basic formula to work out the energy. Alright, I think this is the last question. This looks like the experiment question that usually ends the exam. So how are we doing for time? 56 minutes. Alright, so this shouldn't take more than 10-15 minutes to do. Alright, question 16. Nicola is conducting an experiment to investigate the photoelectric effect using the apparatus shown. Okay, so there's your basic setup. Everyone knows what the photoelectric effect looks like. She uses various filters to shine electromagnetic radiation on particular frequencies on the photocell. So she's got a light source, stick some filter paper there, it makes monochromatic light, and then that light hits the metal plate, and then you've got your photoelectric effect happening. Nicola increases the voltage V until the current reaches 0 and records this voltage. She repeats this process for different frequencies. So when we change this voltage source, we are basically trying to find the stopping voltage. Again, go back to your theory. If this is all gibberish to you, then I don't know why you're looking at this to begin with. This should be done after you learn your theory. So yeah, alright, the variables in this experiment can be classified as controlled, dependent, or independent. Complete the table below by providing one variable from the experiment for each classification. Alright, so controlled. Well, she doesn't look like she's changing the metal plate. That appears to be a constant. So I'm going to call the metal plate control variable. So the metal. What's a dependent variable? Well, let's think about what an independent variable might be. So independent variable might be the frequency of the light because we're changing the frequency using different filters. So the independent variable would be light frequency. And then what is changing as a result of us changing the light frequency? So the light hits the photocell with different frequencies. We all know what happens in the photoelectric effect. It's going to produce a photocurrent. And that photocurrent will be different depending on what color is being used, what frequency of light is being used. And then that in turn will inform us on how we can change our variable voltage source. So I don't know if I want to put the current in the ammeter because it doesn't actually say anything about her looking at changing anything in the ammeter. Well, I mean, it says until the current reaches 0. Look, I'm going to put current. because I actually can't even remember what the examiner's report said. So I'm going to pause this, bring it up, and let's see if we can just verify we're doing things okay. Alright, so here's the report. They've said the dependent is the voltage. Now, look, I'm not entirely sure I agree with that. Because in the question it says the variable voltage source is V, but she increases that voltage V. If it was, she increases it until the current reaches zero and records. Records this voltage. See, I was getting confused between this voltage here, the voltage she's changing, and then the actual value of the voltage at which the current reaches zero. Okay, that makes more sense. That makes more sense. That's why I was confused when I was reading it. So it's the voltage. I think we should be very clear here. Voltage at which current becomes zero, because that's the thing that she's recording. Okay, that's the thing that she's recording. All right, good. I'm glad I cleared that up for myself. Hope that makes sense. All right, use the following information to answer parts B to E. Nicola's results for the experiment are shown in the table below. The uncertainty in the measurement of the voltage is plus minus 0.1 volts. On the axis below, figure 22, plot Nicola's data including uncertainty bars and draw a straight line of best fit. All right, so I'm just going to do this and explain to you what everything needs to look like in order to get the full marks, and then we'll come back in a second. All right, so here's the graph. So 3 marks. Now, you just have to be very careful about where you place these points because the scale's not very nice. So each mark here is 0.125, unfortunately. I would really have liked it if each of them was divided into 5, so each mark was 0.1, but that doesn't happen. So you just have to be really careful with where you place your vertical values, and note that each tail of your uncertainty bars should be plus minus 1.1 volts. Be as careful as you can doing that. Mine are a little bit all over the place, but try and just be super careful. It's a bit hard for me to draw on the screen. But if you've got, the points in roughly the right spot and your error bars are roughly the right size, then you should get your marks for that. The second thing we need is our line of best fit. Now, lines of best fit, you need to account for all of the error bars. Okay, you don't just go through the first and last. For some reason, a lot of people seem to think you only have to go through the first and last pairs of error bars. You kind of have to go through all of them. That's the point of uncertainty. It means your value could have been anywhere within that plus minus 0.1 volt range from your actual measured data value. Okay, so your line of best fit, you kind of have to try and force it to go through all of your error bars. And you just do that as best you can. Now again, it was pretty hard for me to do it on the screen because it wouldn't let me use a ruler, and I had to draw the line and then manipulate it and make it fit as best I could. But with a ruler it should be a little bit easier for you to do that. So I've got my line of best fit here in red. Now, sometimes people extrapolate this line of best fit and continue it on down to here. If you were to do something like that, I might tell you to do it in a dotted line, because you are technically drawing a line of best fit for this data here only. You don't know if the line's going to curve and do something weird. You have no idea. All you can do is fit your line of best fit to the data that you have. So if you're going to extrapolate from this line of best fit, it's best to make it clear that this is a separate line. And I couldn't do a dotted line, so I just did it a different color here. Okay. And as long as you've got those things, you've got the points in the right spot, the error bars the right size, and the line of best fit going through all of your error bars, then you should get your 3 marks. Okay. Everyone's going to have slightly different ways of drawing this, and everyone's going to have slightly different ways of how they've drawn their line of best fit. And so you can imagine if you were to extend that and extrapolate, you're going to have slightly different values for your x and y intercepts. Okay, but the examiners will accept a range, a very small range of values. So long as you haven't stuffed up wildly, you should get the right answer. Part C. So from your graph, determine the value Nicola would find for each of the following. First one is Planck's constant, show you're working. So hopefully from theory you know that when you've got a voltage versus frequency graph like this, that the gradient is going to give you Planck's constant. Don't just assume Planck's constant is a number, you have to determine that number from the graph. Okay. The easiest way to do it is to look at your line of best fit and just try and look at, two definite points that your line goes through. Now, when I did it myself on the paper, this point up here, the line went through that little crosshairs, that little junction, and also through, I'm just going to assume that it's going to go through there, but that would be another little junction that it goes through. Okay, so I've done it like that, and then I checked, actually cross-referenced what I did with the examiner's report. They did exactly the same thing as what I did, so that's fine, that's all good. So I'm going to say that h is the gradient of the graph, which is approximately equal to, because we're probably rounding this thing, so it's y2 minus y1. So according to me, I did this here, so that's my y2, and that corresponds to 1.5. y1 was this point here, over x2 minus x1, come on, line. Alright, x2 would have been there, x2 would have been there, x1 would have been there, so it's 10 times 10 to the minus 11 minus 5.5 times 10 to the minus 11, and that, chuck it on a calculator, 3.33 times 10 to the minus 15 electron volt seconds, which I mean is not too crazy. You're of the same order of magnitude, times 10 to the minus 15, so maybe our data is just a little bit yuck. But that's okay. That's what the data is telling us, so that's what we write down. 3.33 times 10 to the minus 15. Okay. Again, everyone's going to have slightly different values for this. They'll probably accept something in between 3.0 and 3.5. But yeah, everyone's going to have slightly different answers. But so long as your process is very similar to what I've done here, you should get those marks. The second part is a threshold frequency. Again, from theory, that is simply where your line of best fit, if you were to extrapolate it out, would cross over your x-axis. So for me, that happens at 5.5 times 10 to the 14. Did I write times 10? No. I wrote times 10 to 11. Let me just fix this quickly. I don't know why I had minus 11 in my head. Anyway, yeah, 5.5 times 10 to the 14. And the work function, again, straight from theory, it's where your line of best fit would go through your y-axis. So for me, that's about minus 2.8-ish. So I'm just going to write minus 2. Not minus 2.8, 2.8. The minus is a artifact of the graph. Okay, so the work function is just that absolute value of this. All right, so for me, it's 2.8. You might get 2.9, 2.7, something like that. I don't know. All right, for me it's 2.8. Actually, not 2.8. What am I saying? 1.8. We haven't reached 2 yet. That's 1.8. Sorry. All right, explain what information is given about the emitted photoelectrons by the recorded voltage measurements. Okay, so it's, what does this question even mean? Explain what the information is given about the emitted photoelectrons by the recorded voltage measurements. What is this stuff here telling you about the photoelectrons? Okay, what do we know about the photoelectrons if I know these voltages? Again, this is just from theory. You should know that this is the stopping voltage that we've recorded here, and so the stopping voltage is equivalent to the maximum kinetic energy in electron volts of the photoelectrons. Okay, so I'll write it out and then we'll come back. So here we've got the recorded voltage is equivalent to the maximum kinetic energy in electron volts of the emitted photoelectrons. So this voltage gives us information about the maximum kinetic energy of the photoelectrons. Okay, you have to specify maximum kinetic energy, not just energy, not just kinetic energy, but maximum kinetic energy. Okay, it's stopping the most energetic of those emitted photoelectrons. And we're nearly done. So part E, if Nikola had carried out the investigation using a photocell with a plate made from a different metal, explain what effect, if any, this would have had on the graph drawn on figure 22 over here. So how would the graph look different if it was a different metal that she had used? So I would just say something like the graph would be translated up or down with the same gradient. Okay, so the graph I'll just say shift, don't have to be mathematical, would shift up, down, but maintain the same gradient. Okay, or we'd hope for it to have the same gradient, or if not, very close to the gradient that we've measured. Okay, use the following information to answer parts F and G. In carrying out her investigation, Nikola initially used a green filter and produced a graph of photocurrent, I in milliamperes versus voltage, V in volts, as shown in figure 23. Okay, I hope you've seen this type of graph before. She then replaced the green filter with a blue filter, keeping the light output power of the blue light at the photocell exactly the same. Power is the same. Very important. We'll come back to that in a second. Will the position of P here, as shown on the graph in figure 23, move to the left, remain the same, or move to the right? Justify your answer. No calculations are required. Okay, so what's happening? We're swapping out the light from a green filter to a blue filter. Okay, what's the difference between green and blue? Okay, green has a higher wavelength, so wavelength is higher. Blue has a wavelength that is lower. Right? Alternatively, you can talk about frequency. So frequency of green is lower, frequency of blue is higher. Okay, so if we're using light with a higher frequency, we are then now using light with a higher energy, which means that light has more energy able to impart as kinetic energy to those photoelectrons. It can kick them out with more oomph, right? So that means you're going to have a larger stopping voltage needed to stop those more energetic photoelectrons. So you can imagine this stopping voltage is going to increase that way to the left. So we'll say P moves to the left, and why? I will pause and write my explanation and come back. Okay, so I've said blue light has a higher frequency and thus energy than green light, and so more energy is able to be imparted to the photoelectrons, giving them a higher max kinetic energy, and so a larger voltage is needed to stop them, and hence that's why the voltage value increases to the left there. G. Will the horizontal line NM on the graph shown in figure 23 indicate a photocurrent that is greater than, the same as, or lower than the line for green light? Justify your answer. No calculations are required. Okay, so will this line here shift higher or lower or stay the same if we go from green light to blue light? So again, what's happening? Oh, but also because we're keeping the power output the same. What is power? Power is energy over time. Okay. What are we doing to the light? We are increasing its energy. Okay. If I'm increasing the light energy, then we would expect the power to increase. If I increase energy, power obviously would increase, but it's saying that the output power must be exactly the same as it was when we used the green light. So, in order for the power to remain the same, again, you got to think at the physics of what's happening here. Light is composed of individual photons, okay, and it's the sort of totality of all of those photons hitting that metal plate at any given time, or say within 1 second, that tells us what the power is. Now, if I have increased the energy of my light, the only way to keep the power the same is if I'm releasing fewer photons per second, okay? And if I'm releasing fewer photons, then there's fewer photons ejecting photoelectrons one to one, okay? And if I'm ejecting fewer photoelectrons, my current is going to decrease, okay? Because current is a measurement of how much electrons pass a certain point in any second, right? Roughly speaking. Okay, so I can imagine this line will go down slightly, okay? And again, it's because if we're keeping the power constant, if I'm increasing the energy of the light, I must reduce the number of photons being released in order to keep that power constant. Okay, hope that makes sense. Let me write my response, then we'll get back to it. Okay, so again, the line will go lower because for the same power, blue light must produce fewer photons than green since the energy has increased. And fewer photons means fewer ejected photoelectrons, and that means a lower photocurrent. Last question. All right, part H. The results of photoelectric effect experiments provided strong evidence for the particle-like nature of light. State one feature of the results that provided this evidence. Your response should explain both why the wave model does not satisfactorily explain this feature and how the particle-like nature of light does explain this feature. There are three main arguments that you could make here. I'm only going to pick the one that I like, and that is that there exists a threshold frequency. Pardon me, exists a threshold frequency. So a threshold frequency exists. Okay, that is one feature that these results say to us, right? So why does the wave model not explain why a threshold frequency exists? Again, this is all theory. I'm just going to quickly explain this because we've gone way over time. But if you're talking about a wave model of light, then it shouldn't matter what frequency of light you use. If you leave that light shining on the metal plate long enough, eventually enough energy will be built up on the surface of that metal to eject those electrons. Okay? That's what the wave model predicts. It predicts, doesn't matter what wavelength of light you have, what frequency of light you have, if you leave the light shining long enough, or if you make the light bright enough, it will have enough energy to release those photoelectrons. Okay, that's what the wave model predicts. But obviously we've seen that there is a threshold frequency. There are frequencies of light for which doesn't matter what the intensity of the light is, doesn't matter how long you leave it shining on the metal for, nothing is ever going to happen. Okay, so the wave model does not satisfactorily explain that. How does the particle-like nature of light explain this? It basically says that light exists as discrete packets or particles called photons. Each photon has its own energy that's related to its frequency. Simply put, an electron cannot be ejected if the work function of the metal, if the energy of the photon is not at least equal to or larger than the work function of the metal. Okay, if the photon doesn't have at least enough energy to kick that electron out, then it simply just won't get kicked out, and that's what the threshold frequency is. It's the minimum frequency, minimum energy required to kick that electron out. Okay, so I'll just write my answer, and then pretty much we're done, and that's it. All right, so here we go. So I've used one of the key findings that a threshold frequency exists. The wave model predicts that all frequencies should emit photoelectrons given an intense enough light over a long enough period of time, but we don't see that. The particle model suggests that a single photon carries energy proportional to its frequency. If the frequency is too low, there's not enough energy to overcome the metal work function, and so no photoelectrons are emitted, thus a threshold frequency. Okay. There are two other things that you could talk about. I'm not going to go on about them here. Discuss it with your teacher if you want to. The absence of a time delay. Okay, there is no delay in shining the light on the metal and detecting a current. It doesn't matter how strong or dim your light source is, you'll always detect a current pretty much straight away. And the effect of frequency on the energy of the photoelectrons. So if you've ejected photoelectrons, then if you increase the frequency, what's going to happen to the stopping voltage? Okay, why should changing the frequency have any effect on the stopping voltage at all? Okay, so those are the other two things that you could talk about. I'm not going to go on about them here. We've done the exam, and there you go. That's it. Hope you found that helpful. If you like, leave a comment if you've got any further questions. Otherwise, I'll say goodbye. See you later.